Let us try to see whether the formula that we have used to calculate the area of irregular geometry can be applied on a half circle of radius 4 centimeter. I have taken O as the center and OA as the radius or OB as the radius, and a half circle has been drawn. How much is the area of this half circle? Pi multiplied by r square. So, 22 divided by 7 multiplied by 4 centimeter radius multiplied by 4, and since it is half circle, so multiplied by 0.5, it turns out to be 25.1 centimeter square. We will see what if I divide the BA line into equal lengths of 0.5 centimeter, mark point 1, 2, 3 up to point 15, keep drawing normals such as these lines on the BA line, and then keep measuring each of these lengths and sum it up. The sum turns out to be 48.8 centimeter. The average length formula is applied, which is 48.8, and here I took 15 lines. So, divide by 15 plus 1 is equal to 16, turns out to be 2.8 centimeter. Now, applying the formula, area is given by the AB length, which is 4 plus 4 centimeter equal to 8 centimeters, multiplied by the average height 2.8, which is 22.4 centimeter square. Now, we can compare it with the area obtained by formula. It is 25.1 centimeter square, and here it is 22.4 centimeter square. Much difference is found between the two. This difference can be reduced if instead of taking 0.5 centimeter as an interval, we would have taken the distance between these perpendicular lines as 0.1 centimeter. But in that case, as I told you, the time required to calculate the area would have been more. So, we have made a comparison between area obtained by using formula and using the approximate formula. What we did with a half circle, now we are going to do with a rectangle ABCD. In this case, the AB length is 3 centimeter, this is 3 centimeter, and the BC length or the AD length is equal to 7 centimeter. So, the area of the rectangle is 3 multiplied by 7 is equal to 21 centimeter square. Let us find out the area in a different way. Let us divide the BC line here into smaller lines of equal lengths of 0.5 centimeter, and in this way one can draw up to 13 lines. I have drawn up to 7 lines, but line 8 can be drawn, 9, 10, 11, 12 and then 13. The total length is given by, for each of these lines right from 1 up to 13, the length will be equal to AB length, which is 3 centimeter. So, 3 centimeter and 13 such lines is the sum of the length, which is 39 centimeter. Now, to find out the average height, sigma L divided by L plus 1 we have to do, which is 39 divided by 13 plus 1 equal to 14 is equal to 2.8 centimeter. So, the area of the rectangle using approximation formula will be 2.8 centimeter multiplied by the BC length, which is 7 centimeter, which turns out to be 19.6 centimeter square. Now, you can compare, the true area is 21 centimeter square, whereas using approximation formula I have got 19.6 centimeter square. A question comes frequently in mind. I have considered line 1 up to line 13, but what about the AB line? Why I did not measure, and what about the DC line? We are going to take two cases where along with these 13 lines, AB line as the 14th line and DC line as the 15th line will be taken, and we will see whether a variation from this area is happening, and in another case out of these two any single line will be taken and the area will be checked. Let us consider the AB line and DC line. So, the number of vertical lines here increases from 13 to 15. So, the total line length is 15 multiplied by 3 is equal to 45 centimeter. To find out the average height, sigma L 45 divided by L plus 1, here it is 15 plus 1 is equal to 16 is equal to again 2.8. This number is same as that Therefore, the area turns out to be 7 multiplied by 2.8. From where 7 is coming? 7 is the BC length, and again 19.6 centimeter square. So, it does not matter whether I take AB line and DC line in the calculation or not. Now, let us take only one of them, either AB or DC. In that case, the number of such vertical lines is 13 plus 1 is equal to 14, and each of these lines of 3 centimeter length, because the AB length is 3 or the DC length is 3. So, it is 42. Now, the average height formula wise is sum of all these lengths, which is 42 divided by L plus 1, and here it is 14 plus 1 is equal to 15, and interestingly again we get 2.8 centimeter. So, in this case the area also is 7 multiplied by 2.8, same as 19.6 centimeter square. Let us do this exercise for our clarity. We want to find out the area of this irregular geometry. One of the lines in the boundary AB is a straight line, and in my drawing it is 6 centimeter long. Now, I have drawn 11 vertical lines on the AB line, and each of these vertical lines are 0.5 centimeter away from each other. All these lines are summed up lengthwise, and it is 18.5 centimeter. Now, I divide 18.5 by 11 lines. So, 11 plus 1 equal to 12. So, I find out the number average height is 1.54 centimeter. Multiplying this average height by 6 is the AB length 6 centimeter, we find area of this irregular geometry to be 9.24 centimeter square. Now, apply the same formula, and in this case what additional thing is being done, I consider this line also as a 12th line, which is originally a margin of the irregular geometry. So, in this irregular geometry there are two straight lines, one is AB line, another is BK line. The BK line is considered. So, the number of lines are 12, in this case L plus 1 will become 13, and whatever the sigma L was found 18.5 centimeter, I will add up the BK length, which is 3.1 centimeter, and I find out the average height to be 1.66 centimeter, and note that this 1.66 is different from 1.54. Since this is little more, I am going to get little more area of the irregular geometry. How to get area is equal to 1.66 multiplied by AB length, which is 6 centimeter, which is 9.96 centimeter square. As I said, this area is little bit more than that area. Now, students can try to draw these vertical lines at 0.3 centimeter interval to get more accurate area. Let us revisit the kink method. In the previous example, few lectures back, I have demonstrated a case where the lithological contact in the left hand side is dipping at a gentler angle than that at the right hand side, which is dipping at a steeper angle, and both of them are dipping towards the same dip direction, and I write say x degree north. A slightly different version of the problem we will do, where the left hand side lithological contact between the rock P and Q is dipping at a steeper angle than the contact between Q and R, which can be found if one moves towards m degree geographic north. The lithological contact P and Q and the lithological contact between Q and R have the same dip direction, which is m degree north, which can be say 30 degree north or 190 degree north. Now, we are going to apply the kink method. So, what is the fundamental difference between the problem I am going to tackle right now and the one which was tackled earlier? In the earlier case, the left hand side lithological contact was dipping at less angle than the right hand side, whereas in the present case, the left hand side lithological contact is dipping at a steeper angle than that in the right hand side. Same process is to be followed here, but for the drawing purpose, the easiest approach would be to take this page and take a 180 degree turn. So, I have done upside down, and the problem is now just same as what we did earlier. So, the known process of work can be applied. So, these 2 points can be joined. This steeper lithological contact can be extended upward in my diagram, but actually if I flip the page it will be downward. Next, point M and N can be joined, and this angle we need to find out. This angle in this case is 54 degrees, and I will draw 54 degrees from this side, and I reach point D such that the MD length is equal to the ND length. Next, this lithological contact I will move up and touch point D and will draw. Next, say this point is small t, the small t, then capital D and N, this angle is to be found out. In my diagram, this angle is 145 degrees and half of this amount is equal to 73 degrees. I have to draw 73 degrees angle, or in other words I have to bisect the angle TDN by a straight line. So, this angle is 73 degrees and this angle is 73 degrees. This bisector is going to be called as the axial trace and it intersects this lithological contact at that point. From that point I have to draw a line parallel to the other lithological contact, and in this way we say that the fold is constructed by the kink method, where the limbs are marked by pen for clear understanding. It is same as what was done in one of the previous lectures. Now, I am going to flip the paper because that was the starting point. So, here the fold is ready. Now, you can compare this fold where this line is the axial trace with the kink method applied on this diagram in one of the previous lectures. Suppose by kink method of reconstruction, a fold is to be reconstructed here. The lithological contact between P and Q is shown, that between Q and R is shown, and that between R and S is shown. And the dip of the contact between P and Q is less than that between Q and R, and the dip of contact between R and S is less than that between the contact Q and R, whereas the dip of the contact between R and S is more than also that between P and Q. So, I can write here, this is the situation. In other words, this contact has got the highest dip, this contact has the intermediate dip, and this contact has the lowest dip, which is represented in this writing. Let us try the kink method. Let us join the AB line and extend this lithological contact. This is one of the earlier lectures done by me. Let us find out this angle 45. So, from here I have to draw 45. So, this is the point D. I have not drawn the AD line, D is drawn, the length DA is same as DB. Now, what to do? From point D I have to draw a line parallel to this lithological contact. Done. Now, call it K. The angle KDB is to be bisected. How much is angle KDB? Let us find out that one first. 146 degrees, its half is given by 73 degrees. I have drawn that 73 degrees angle. Next, this axial trace intersects the PQ contact over here. From that point I will draw a line parallel to the contact between Q and R. So, this portion of drawing is over. Now, I am going to see the contact between Q and R and the contact between R and S and want to execute the work. To do that, I will flip the paper. Now, same process here, I will extend this up or basically down, since I have flipped the paper, join the BC points, find out this angle which is here 48 degrees. So, from point C I have to draw 48 degrees angle. By doing that, I have reached the point D dash. Now, from point D dash I have to draw a line parallel to this lithological contact. Next, I have to bisect the angle KD dash D. How much is the angle? 166 degrees. So, its half is given by 83 degrees. So, this is another axial trace and this contact is drawn through this point. So, in this way we have finished the drawing. Now, I am going to flip the page. I am going to extend this axial trace up and I am going to draw this axial trace down. Actually, they do not intersect in this paper, it goes outside, no problem. Now, what to do? This particular line I will draw down here, then this particular line I am going to draw up, where this line intersects this axial trace over here. From that point I will draw a line parallel to KD line. So, first let us set the KD with the 2 set square. Now, here we go, I have done. Now, and another thing is this line where it intersects the axial trace here, from here I will draw a line parallel to KD dash. I also called it K, let us call it K dash. So, K dash D dash. So, here it is going to be K dash angle. So, in this way the construction has been finished. I am now going to draw the lithological contacts which is kink folded by a pen, so that things become clear cut. Now, if I want to define the deep domain, in this side of the axial trace is deep domain 1, between the two axial traces is the deep domain 2, and in this side of the axial trace is the deep domain 3. In deep domain 1, all the layers have, all lithological contacts have similar deep and deep direction. In deep domain 2, they have similar deep and deep direction, actually the same deep and deep direction, and in deep domain 3, they have same deep and deep direction. In this particular case, the deep direction in the deep domain 1, deep domain 2 and deep domain 3 are all towards the same geographic direction. Say this is L degree geographic north, so it is the same, but the deep amounts are different. How much is the deep amount for this deep domain? If I am able to draw a horizontal line, then this angle, whatever comes out by angle measurement, would be the answer. Within this deep domain, if I draw a horizontal line, then here is the answer, and within the deep domain 1, if I draw another horizontal line, then this angle is the another deep amount. The deep amounts are different, but the deep directions are the same. Clearly, this is the lowest deep amount. Let us measure it, and the deep is here 5 degrees. In this case, the deep is 24 degrees, and in this case the deep is 35 degrees. So, here we have the lowest deep in deep domain 1, we have the intermediate deep in the deep domain 3, and we have the highest deep. This is also in tune with the starting deep amounts. Let us revisit how to find out the depth of center of curvature in the case of Busk method of fold reconstruction. We first of all consider an ideal situation of a horizontal surface Mn. Consider Mn is a horizontal surface, and on that at point A and at point B, the lithological contact between units P and Q and Q and R were obtained. These contacts have been drawn here and here. The deep at the contact A between lithologies P and Q is say theta 1, the deep at the contact between Q and R at point B is say theta 2, and in my drawing theta 2 is more than theta 1. Later students need to derive the formula of the depth of center of curvature when theta 2 is less than theta 1. This is your homework. Okay, back to the problem. Now, we draw normals O1B on the contact here, contact between Q and R, and we drop another normal O1A on the contact between lithologies P and Q. Now, we draw a vertical line OO1. Since OO1 is a vertical line and MN is a horizontal line, the angle between them is 90 degrees. OO1 is a vertical line. Now, consider triangle OO1B, OO1 and B. Within this triangle, this angle is equal to 90 degree minus theta 2. Why? Because this angle is 90 degrees, O1B is a normal, and this is theta 2. So, this angle is 90 degree minus theta 2. Similarly, this angle here has to be 90 degree minus theta 1. Now, back to the triangle OO1B, the OO1 length here divided by this length is equal to tan 90 minus theta 2, which is cot theta 2. So, from here I can write OO1 is equal to y plus x multiplied by cot theta 2. Now, I will take triangle OO1A. This is O1 and this is A. Here OO1 divided by y, again OO1 this line divided by y. Y is the distance between the OO1 that intersects on MN line at point O and point A. So, this is y distance. So, OO1 divided by y is equal to tan 90 degree minus theta 1, tan of this angle, which is cot theta 1. So, from here I can write OO1 equal to y cot theta 1. Now, I have got OO1 equal to something, OO1 equal to something, I can equate these two. After equating, I can obtain the y value, and it is x cot theta 2 multiplied by cot theta 1 minus cot theta 2 to the power minus 1. Putting this in equation 1, we find OO1 is equal to xy cot theta 1 cot theta 2 multiplied by cot theta 1 minus cot theta 2 to the power minus 1. So, what we have obtained? OO1 is the depth of the center of curvature, because taking O1 as the center, we draw two circular arcs like this and that, and the Busk method gets completed. So, in this way the depth of the center of curvature has been obtained. Consider a case when on a horizontal surface there is a steeper contact and that is a gentler contact. In that case, we can draw the normals. Then the center of curvature lies above the ground surface. This is ground surface. By the same process, we can find out this height as well. This problem I will initiate, I will request the students to think about. Say on the ground surface, this is the ground surface GS shown by this blue pen. At 2 points A and B, the lithological contacts between rocks P and Q and R have been drawn. The situation is such that the depth of the contact between P and Q is less than the depth of the contact between Q and R, and both these contacts, this and that contact dip towards the same geographic direction, say B degree north. The main difference from the previous problem is that in our previous case, the AB line, once it was joined, it was a horizontal line, but in this case once AB is joined, it is defining actually RS or the regional slope. If I join AB by a straight line and if I draw a horizontal line H, then this angle phi, which is shown here, can be called as the regional slope. Now, suppose the Busk method is applied, can you find out the depth at which the center of curvature will come? A hint to do this problem is that extend this contact and this contact intersects the horizontal line at B dash. If A and B dash were the starting condition, we have already seen how to find out the depth of center of curvature. So, in this case, from the given information that phi is the regional slope, and say by some way we know the AB length as Z, this length is Z. If we can find out the AB dash distance, that is what I am writing. If it can be found out, then we can go back to our previous problem. So, to students, find out the AB dash distance from the given information, where Z is this length, phi is the angle. There are other two angles, theta 1 and theta 2, that I will draw now. If I extend this horizontal line, this angle is theta 1 and this angle is theta 2. So, we have good constraint on the different angles of this triangle, and we know one of the lengths. Can we find out the other length? If that is found, then we can go back to the previous problem.